Hey everyone, welcome to another free prep hour. I am your host, Tyler Johnson, and I am an instructor and tutor with Manhattan Prep. And these prep hours are an opportunity for us instructors to go deeper on a topic that we don't normally do in the regular course. So, yes, we talk about averages, but we're going to go heavy into it today. We'll be looking at weighted averages and some other cool techniques to approach these problems. And if you've never been to one of these before, the way they work is we have this session being conducted live in a Zoom room right now, but you also might be watching on YouTube from a recording that gets thrown up usually 2 weeks after it's hosted there. So big welcome, whether you're here live in the room now or you're watching on the internet at a later point in time. If you are live in the room with me, go ahead and chat in the Zoom chat box. Tell me what city you're connecting from, and we'll get a quick poll of the spread. Myself, I'm in San Francisco, California, where it was kind of a stormy day. I hope my internet doesn't drop out here. I think we'll be okay. I think the worst is over. We got Phoenix, Arizona. I grew up in Albuquerque, so shout out to the desert Southwest. We got Oakland, California. We have some other Bay Area residents here. Love to see it. And we got DC on the East Coast. All right, so no one in Central Time, but we got a good swath of the US covered. Cool. So thank you all for being here. We're going to start pretty simple, and then we're going to get into some harder material as we progress. So just to kind of warm up here, here's today's first problem, just kind of understanding the basics of averages. Go ahead and tell me what would be the average of this set. And to calculate an average, you got to know this formula. It is the sum of the terms divided by the number of terms. So these five numbers sum to 20, so the average would be 4. So before going any further, make sure you're comfortable with that formula. That's kind of as simple as averages will get on the test. I'm going to show you a problem that's a little trickier, but you can still be successful here, just applying that same formula. Try this one out and tell me the answer for this problem. And fundamentally, this problem is still an application of average being sum divided by a number of terms. But this time, that sum piece is going to be a little more complicated because you have 9 scores of 100 and then this unknown 10th quiz grade. So the ultimate average is 96. There's 10 quizzes in total, and the sum is going to be 9 times 100, or 900, plus that unknown value. And once you have that set up, all that's left to do is solve out for x, and you should get 60. And this is all kind of building up to a more complex average concept we call a weighted average. So at the bottom of your screen, I'll give you this formula. The weighted average is equal to weight 1 times value 1 plus weight 2 times value 2, all of that divided by the sum of the weights. And if you've not heard those terms before, a weight is basically the number of times a value happens. Or if you have the units of the problem involved, it's always going to be in the format of value per weight. Right? In the previous example, we had score per quiz, where the number of quizzes, that would have been the weight, and the scores themselves would have been the value. So here's a new problem. Go ahead and read this one, and I'll kind of walk us through the solution together. And some of you may be able to kind of intuit what the answer to this is. And we'll talk more about intuition and using logic on these problems, but for now, I want to get more practice in with the formula approach. So we don't know what the final quiz average is. That's going to be the x that we're solving for. But we do have these weights here. It's an even 50-50 split. So you could use 50%. I prefer fractions, so I'm going to do 1/2 and 1/2. And then the values involved, half the scores are at 100, and the other half are at 90. So in the denominator, the two halves are just going to sum to 1. The half of 100 and half of 90 give you 50 and 45. So the final average is 95, right in the middle. Again, you might have intuited that. We'll get to that in a second. The GRE is unlikely to present something that straightforward when it comes to weighted averages. What you're more likely to see would be an example like this. So I'll give you all a few minutes here. See if you can apply the formula, and then chat your answers to me if you're here in the room. Okay, here's the setup for this problem. This time we know what the ultimate weighted average should be. It's going to be 96. And we know the two values. We've got some scores at 100 and some scores at 90. And of those 100, we had 6 scores. The unknown here is where it says 90 on the rest. That's what we need to figure out. How many scores were at 90? So that X weight is going into the numerator and the denominator. Once you have that set up, you're going to solve for X. And the way to start there is clear that denominator and multiply both sides by 6 plus X. And then from here, 96 times 6, that's pretty difficult. I can't really do that in my head. So I'm going to reach for a calculator. And I'll get 576. And then I just keep continuing to solve for X. And you'll get 4. But careful, that doesn't mean the answer is 4. Remember, the ultimate question here is how many tests did she take in total? Not how many were scored at 90. So the correct answer is going to be 10. Okay, let's look at one more problem using this formula, and then we're going to talk more about using logic for these kinds of questions. Here it is. For the setup here, we again know the final weighted average. It's 92 in this case. And I know both the weights. We've got 90 on the first 10 and then some score at the final 5. It's that what right there. What must she average on the final 5? That is the unknown we're solving for. And once you have it set up, then you want to first multiply that denominator. So multiply 15 across each side. And again, 92 times 15, that's a pretty difficult calculation. So I would use the calculator for something like that. You'll get 1380, keep solving for x, and you should get 96 as the final answer. And when it comes to this weighted average formula, what I really like it for is it's precise. You will get an exact number when using this method. So that kind of makes it ideal if it's a numeric entry problem where you're filling in the box, or if it's a multiple choice problem. And actually that should say clustered multiple choice, right? When all the answers are really tight together, you can't really afford to estimate as much. You need that precision when the answers are all very similar. What I don't like so much about the formula is it tends to be a little slow, right? There's going to be just a few steps of algebra to plug my way through it. And it often needs a calculator, which can, again, slow me down. And I don't know, using a digital on-screen calculator for the GRE, it's clunky, and it's really easy to punch in the wrong number accidentally, and then you have to start over. And I don't like using the calculator as much. So if I can avoid it, I try to. And that's where I can start to take a more intuitive approach rather than relying on the crunchier formula method here. So let me talk a bit more about that. And the way I like to intuit and use logic for a weighted average is I just kind of think of it like a scale. So the kind of bar of the scale, it's basically a number line with the two values. And you want to note the exact midpoint between those two values. And in a system, if the weights on those values were exactly equal, I had the same weight on the left side, same weight on the right side. In a system like that, your weighted average will be at the exact midpoint. But most questions on the GRE, they're not going to be that comfortable. What's going to happen is one of the weights will be bigger than the other. And if I left the weighted average in the middle, that would create unbalance in the system. And in order to bring it back into balance, what has to happen is the weighted average is going to slide towards the side that has more weight. So I like to say the weights have gravity. Whatever side of the system has the heavier weight, it pulls the weighted average towards that side. So let me give you a demonstration of what this could look like for those examples with Anna we just talked about. So in the first example, when it was 50-50, that's the easiest imagining here. My two values are 90 and 100. I have half my scores at each of those values. So because it's equal weight, the weighted average is going to be right in the middle, the same place as the general midpoint between my two values of 90 and 100. So when things are equally weighted, your weighted average is in the exact middle. But when things aren't equally weighted, like in the second example, if I wanted to use this scale approach, I know I've got a weight of 6, right? 6 scores of 100. And then I've got this unknown amount on the left. But the midpoint here is 95. My weighted average is closer to the right. So what does that allow me to say about this weight on the left relative to the other numbers I do know? Well, if I have 6 over here and the weighted average is closer to that value, that has to be the bigger weight. So this weight on the left side, it'd have to be something smaller than 6. And if this were a multiple choice problem, the odds are there'd only be a single answer under 6. So I would just pick that one and move on to the next. Or if this were a quantitative comparison problem, I'm really just trying to compare like quantity A to quantity B being 6, something like that. I don't need precision if that's the goal. So when it comes to this scale approach, the downside is it's less precise. The good news is it's faster, and it's great for quantitative comparisons or spread out multiple choice. Right? It's always best practice. Look at the answers before you start solving and note the format and note the spread. Are things really clustered together, in which case you're going to need more precision, or are the answer choices more spread out, in which case you can be a little looser with it and use a faster approach like this. I could even use this approach on the third example. It's a little trickier here, but I'll show you what I would think about. So this time we don't know what the value on the right side is going to be. But what I do know is the weighted average is going to be 92. And bear with me for a second. I know there's 10 scores at 90. In the original problem, they said there's 5 scores at the unknown amount. I'm just going to imagine for a second that it's an equally weighted system. So imagine the equal weighted scenario. If I had a 10 for my weight on the right side, what would this number have to be? Yeah, I see some of you have this right in the chat. If it were equally weighted, it'd have to be 94. Because then my weighted average has to be the exact midpoint between my value on the left and my value on the right. So after you imagine the equally weighted scenario, morph that into the actual scenario. Because in the real version of the problem, I don't have 10 scores on the right. I only have half as much. So what does that enable me to say? If I only have half as many weights on that right side, what must the actual value on the right side be respective to 94? And you'll see it must be something greater than 94, right? This number has to slide out further right to ensure the bigger weight on the left is closer to the weighted average. And again, if it were multiple choice, there's probably only one answer bigger than 94, and I'm picking that one, and then I'm done. I don't need to know what the exact number is. I just need to pick the one that's bigger than 94. Okay, so those are the basics to the scale approach. You want to draw your beam, put those values on the beam, note the exact midpoint between the values if the values are known, and then from there, the weights have gravity. Whatever side has more weight on it, it's going to pull the weighted average towards it. So let me have you all practice this idea on your own. And I want to acknowledge too, the first time I was shown this, my brain was a little blown. It's not necessarily the most intuitive approach, but I would just say it really pays dividends. You are able to answer weighted average problems much faster using this scale metaphor versus the average formula. So even if you aren't the best at it right now, I encourage you, try it out on these next few problems, try it out some more on your own at home and see if you can get better at it, because it really allows for some quick solutions. All right, here's a new problem. Try it out. So in reading this problem, it's a weighted average problem. It's a quantitative comparison. So that's kind of crying out to use this scale approach. And if you're confused about should the citizens be the weight and the salary be the value, which way does it go? Remember to think about the units. In this problem, what we're looking at is the salary per citizen. So salary is going to be the value, and the number of citizens is going to be the weight. So on one extreme, you have salaries of 45,000. On the other, you have salaries of 55,000, which means the exact midpoint in between those two would be 50,000. And most of the time on the GRE, quantity B in a problem like this will be equivalent to the exact midpoint. So you just need to figure out what side of this system has the bigger weight. And at the higher salary, I have 66,000 citizens. And at the lower salary, we have more people. There are 73,000. So that side's got more weight. That's the side with the gravity. So from that midpoint, my weighted average is going to get pulled under 50,000 to the left. So the average salary, I don't need to know the precise number. I just know that it's under 50,000. So the answer is choice B. And note that if you wanted to, you could use the formula here. It definitely works, but just look at how much more work it would take. If it were numeric entry and I needed that precision, I'm definitely using it. But for a quantitative comparison, I think this is overkill. It's too many steps, it's slower, it's easier to make a simple mistake. So when possible, I always prefer that scale approach instead. Okay, let's look at another example where I think that scale approach comes in really handy. Try this one out. So we've got these two machines, X and Y. X fills bottles up at 584 milliliters per bottle. Y fills them up at 594 milliliters per bottle. And note, 584 and 594, they are 10 units apart. So that means the exact middle would have to be 5 above X and 5 below Y at 589. So now I need to just plot where that average value lies. So if it's at 590, it's a little to the right of the midpoint. And if it's to the right of the midpoint, there must be more weight on the right side and less weight on the left side. And that tells me machine Y over here, that's the one with the bigger weight and the bigger number of bottles. So again, I don't need to know the exact number of bottles. Most quantitative comparison questions, you're just trying to figure out, is it bigger or is it smaller? And that's the real strength of this approach. So we've looked at a couple quantitative comparisons. I also want to show you a regular multiple choice problem where I think this approach works well. So take a look at this one. So after reading this problem, the first place I'm going to start is giving the answer choices a glance. And what I see is they're pretty spread out. I go from 10% to more than double that, up to 26%. So the fact that they are that spread indicates I can be a little looser. I can estimate I could do something like the scale approach. If my answers had been more clustered together, like 14, 14 and a half, etc., choices like that are more clustered. That tells me I need to be precise. I can't afford to use the looser scale approach. I would want to use the formula and get an exact value. Fortunately, that's not the case here, so I'm good to proceed with the scale approach. And the units here, I've really got this concentration per gram. So it's that percent of alcohol is the value, and then the weight here, it's the literal weight in grams. So on one side of my beam, I've got the low value of 8%, and then the max value of 18%. And even if I had to take a guess on something like this, there are two answer choices that I could get rid of immediately, right? Two choices would be very poor guesses. Those two are D and E. In a weighted average problem, I can never have a final weighted average that ends up outside the range of the values. It's got to be somewhere in between 8 and 18. 19 and 26, those are both somewhere outside. So those are impossible. Now my midpoint between 8 and 18, I'm just taking the average, the simple average of 8 and 18 themselves. And that'll be 13%, right? 5 above 8, 5 below 18. And in terms of the weights, we have 3 grams over here at the smaller concentration. And then a whopping 7 grams. We have more than double on that right side. So from 13, the weighted average will get pushed further right, and check out those answers. It can't be lower than 13. It can't be 13 itself. It must be C. And that's generally the case on a multiple choice weighted average question. As long as you notice the choices are spread out, you can be loose with it. You can just think about the intuitive scale and avoid having to do the crunchy, precise calculation. So let's switch gears. I know we went hard on weighted averages there. I want to show you another average concept. So say we have this set of 4 numbers, 0, 1, 4, 7. They sum to 12, so the average is 3. And the concept here is that the distances from the average of these set members, it has to be equal distances both above and below the average. So when compared to the actual average of 3, notice that 0, that is 3 terms, 3 units below. 1 is 2 units below. 4, that's 1 unit above 3. 7, that's 4 units above 3. And those sums come out the same. So you've got this total distance of 5 below the average and 5 above the average. And that would work too, even if I had an odd number of terms. If I expand this set a little bit, if I include a 13, now I'm getting a bigger sum of 25. Now I have 5 numbers. So the average here is going to be 5. And compared to 5, that first number of 0, that's 5 units below. 1 is 4 units below. 4 is 1 unit below. 7, 2 above. 13, 8 above. But things are balanced. You've got a total sum of 10 below and 10 above. That's how you know 5 is the average. And you can use this thinking to save yourself some time when you already know what the average is and you're trying to figure out what one of the set members may be. So here's an example where you can use that logic. Try this new problem out. So I know the total average here is 74, and I have 3 known set members of 75, 82, and 84. So 75, that's 1 above my average. 82 is 8 above the average, and 84 is 10 above the average. So in total, I have 19 different members, a total distance of 19 above the average. And below the average, I have 0 right now. So things are not balanced. I got to have something that is 19 below 74. So 74 minus 19, that gets me the correct answer. Oops, not of 44, of 55. And full disclosure, you could also approach this using the general average formula. Here's what that solution would look like, but it's just a lot more steps. The numbers are a lot bigger. So again, I find that thinking to be a little more error prone. Whereas what I've shown here, the numbers are just much smaller and easier to digest, and it's just a little more intuitive. Okay, let's look at one more example like this, and then we'll talk about something a little different next. In this example, we are starting with an average of 84. And I know that there are 12 quizzes averaging out to 80. And 80 is 4 units below 84. I've got 12 of those scores. So in all, I've got 48 units of distance below the average. So to counteract that and keep things balanced, I must have 48 units of distance above my average. But I only have 4 quizzes to do that with. So those 4 quizzes, if I'm trying to get a total sum of 48 above, then they must be 12 units above each, because 4 times 12 makes 48. So starting at 84, I add 12 units to that, and that's how you get the correct answer, 96. Okay, for this next problem, I'm just going to kind of toss you into the deep end here. I'll show you a special formula that works well for it after you try it on your own. Here it is. All right, so I've seen a few variations of a setup like this in official materials where there's an average provided, but then it's discovered that there was an error constructing that average. So then they give you the corrected numbers and they ask you to figure out what's the new actual average. For a situation like this, if you want a tidy formula to use, your new corrected average is going to be equal to the old average plus whatever has changed in the numbers divided by that number of terms. So you're just kind of spreading that general change across the exact number of terms. So in this problem, the old average Bob originally calculated was 15. And then the change here. Specifically, you want the change to be the new value minus the old value. So the new number should be 0. The old number, you accidentally wrote down 300. So I've got 0 minus 300, but the actual number of boxes hasn't changed at all. That's still 100. So you've got 15, and then minus 300 over 100, that's going to be minus 3. So your new answer is 12. And where this thinking really pays off is if you have a data interpretation set and there were 100 different numbers used constructing the average, you don't want to have to really add up all of those 100 numbers all over again. Instead, you focus just on what's changed, right? The new value minus the old value, and divide that by the number of terms, and then combine it with the previous average. All right, so an hour has gone by. It's been a fun time. Hope you all learned some things. To kind of recap what we talked about today. First of all, you've got your basic average definition. It's your sum divided by the number of terms. Then for a more complicated example, when you've got multiple values, multiple weights, that's where you use your weighted average formula. And specifically, if I know I need precision, if it's numeric entry or it's multiple choice and things are clustered together, that's where I'm pulling for the formula. If, however, it's a quantitative comparison or a multiple choice question where the answers are further spread out, I don't need as much precision. I can afford to be a little looser and faster with it. And that's where I prefer to use that scale logic. Additionally, we talked about this idea when you have an average, the sum of the distances of the set members to the average, you have to have an equal distance both above and below. And as we just saw in the previous problem, if you see a question where there's an average being corrected, you can use this formula here. And if you enjoyed today's session, there are going to be more in the future. If you go to that link on screen, that's how you can find future free prep hours, as well as an opportunity to take one of our classes for free. So at Manhattan Prep, we teach a 9-session GRE course. Session number 1 is open to the public, so if you want to check it out sometime, head to that link. There should be a link in the video description as well. But yeah, hope to catch you again sometime in the future, either at another prep hour or at a free trial class. So thank you all for being here. Enjoy the rest of your day.